Hello, we are Buller Bias, and this is our first system acceptance review. We've been working tirelessly since our club's founding 6 years ago to build our first rover dubbed Sisyphus, and this year we are submitting our first system acceptance review in club's history. This year we restructured our team from 6 project teams to 3 technical sub-teams, a hardware team, electrical team, and a software team, as well as a business/operations team.
This year, the mechanical team completely overhauled the rover's biopayload and robotic arm, focusing on biopayload's functionality and the robotic arm's load capacity.
For the chassis, we improved upon last year's suspension system. The front wheels now utilize a spring-based suspension, while the rear wheels pivot on a reinforced joint for better terrain adaptability. We also tested and 3D printed custom TPU wheels to enhance mobility and provide additional suspension support over rough surfaces. The robotic arm required significant upgrades for precision and load capacity. The original worm gear-driven joints lacked the accuracy needed for fine control, so we reworked them and added additional belt tensioners for precise articulation. We also tested multiple end effectors to optimize task performance. With these upgrades, the arm is now capable of lifting over 5 kilograms with stability and precision. The biopayload system was completely redesigned for modular functionality and efficiency. It is now divided into 2 key components, the carousel system and the auger system. The carousel system handles the life detection task. With these upgrades, our rover is now fully functional, modular, and capable of handling all University Rover Challenge science and mobility challenges.
The electrical team implemented better wire and circuit management for more optimal power distribution.
We created a new PCB design for the power distribution board for the robot. The board consists of 6 layers and is responsible for distributing power to the robot arm and the rest of the robot. The board provides pathways for both 12 volts and 5 volts power and includes 45 test points to make sure each component receives power at the correct times and at the correct level. For BMS, our original lithium-ion battery was discharged from not using it in over a year. As a temporary replacement, we used 2 6S LiPo batteries in the meantime for testing. To complete the biopayload task, we used an Arduino Mega to primarily test components, including our temp sensor, nichrome to heat solutions, magnetic stir bar, pumps, and stepper motor for controlling our carousel with the different test tubes of solutions. Post-SAR, we will be focusing on making permanent connections.
First, the arm picks up the soil and moves it into the tank. Then, the pump pumps the soil and water solution from the tank into the test tube. Next, the motor rotates the carousel with the test tube. Then, the webcam will capture videos of the 3 tests for life in the soil we have to perform. First, we use Benedict's to test for simple carbohydrates. Then we use Lugol iodine to test for starches. Finally, we use ninhydrin to test for amino acids.
This year, software team focused on integrating all components together, for example, controlling motor by remote operation and autonomous navigation algorithm.
For autonomous operation, we implement auricle detection algorithm from set2 camera in front of the rover. Since set2 is stereo camera, the algorithm also has the distance of the auricle tag and will stop at the desired distance. The depth information will be used in detecting obstacle and collision avoidance. The set2 is the main sensor where the auricle tag is on site. For most of the navigation, the rover will use GPS information and the IMU to reach the target location. On the rover, we use JSON or Nano as a main computing unit. We connect the JSON with Ubiquiti Rocket M2 that will wirelessly connect to another Ubiquiti Rocket M2 at the base station. The remote operation, the operator will have the first view vision provided by the set2 stereo camera that is mounted in front of the rover. Our rover is driven by 6 BIDC motor. To control motor, we use ODrive as an electronic speed controller. One ODrive can control up to 2 motors, so we put 3 ODrive in total. We connect the front 2 motor to one ODrive, then connect the remaining 2 motors on each side. From the software perspective, we group motor into left and right side. Each side has 3 motors. Then we use differential drive configuration to control the movement of the rover. There is another RGB camera at the end effector of the robot arm. This camera helps operator to see cross-range vision when operating the arm.
We are confident in our rover's ability to succeed at the final competition, and so we are excited to showcase our first ever rover at the 2025 University Rover Challenge Finals in Utah. See you all there.